Good day, everyone. I am Nattapong Hatchavanich from KMUTT. Today, I would like to talk in the topic of wireless power transfer for electric vehicle. And this is the presentation outline for today. The wireless power transfer system, or we can call the WPT, use the principle of magnetic coupling to transfer power across the relatively large air gap. The WPT system consists of the rectifier and filters, followed by the DC to AC converters supplied through the primary coil and the magnetic field induced to the secondary coil converted to the DC value by the AC to DC converter to charging the batteries. So the output power is dependent on three parts: the frequency and the coil current, which related to this converter, inverter, primary side control, and the compensation circuit. The mutual inductance and the secondary coil inductance. Many publications provided the power path design for maximize the mutual inductance. And finally, the load quality factors, which related to the secondary side control. Some publication introduced the converter on the secondary side, which can be maintain the output voltage under the air gap distance variations. The reactive power compensation, or we can call it known as the resonance circuit. The reactive power compensation is commonly chosen to overcome the issue of poor magnetic coupling. The four basic compensations circuit, which consists of series, parallel, and a parallel series, or we can call SS, SP, PP, and PS. Yeah, with the following advantage in the table. In my research, the PP compensation is selected because it can provide constant voltage with low input current requirement. But you can see in the table, unfortunately, operation at the resonance frequency of all conventional compensation techniques, the voltage or current depends on the coupling, which related to the misalignment position and the air gap distance. Now the PP compensation circuit is selected, and we would like to find all the hidden operating frequencies. The all possible operating frequency is obtained by setting the imaginary part of the input impedance to 0 and solving to find for the omega. There are three operating frequencies. The omega 0 is a conventional resonance frequency, as that, and it's always exists. The omega 1 and omega 2 can be possible either real or complex. Only real number of the omega 1 and omega 2 will provide the operating frequency. Since the parameter variations, it can turn from complex to the real number. For example, in these figures, the coupling variations, since the coupling increase above the limit, this critical coupling, the operating frequencies splits from omega 0 to omega 1 and the omega 2 in the red line. This behavior known as bifurcation. Consider at the voltage gain at each operating frequencies. The voltage gain at the resonance frequency depended on the load and coupling. The voltage gain at omega 1 and omega 2 is equal to the square root of the inductance ratio. You can see in this block, in this equation. It's very magical. It is free position. Is that possible? Previously on the analysis, the voltage gain is independent from the coupling, which related to the coil position. This page shows some of the experiments. We use the light bulb connected to the end of the secondary side. The left-hand side is the WPT system with the traditional operating point with non-bifurcation. You can see in the video. The voltage is decreased when the coil is misaligned. You can see in this video. And with the proposed control with the bifurcation operation, you can see the voltage is approximately constant during the moving of the secondary unit. This because of the leakage flux is minimized. You can see the result in the finite element simulations. There are some of leakage with of the non-bifurcated operation, but with the proposed method, the leakage is minimized. By this strongly advantage, the proposed system can modify with a small electric vehicle. The output of the WPT system connected to the onboard chargers on the vehicle, and this is the result under the abrupt misalignment. The secondary coil is suddenly moved, and the primary and the secondary voltage remains constant. You can see in this. Only the frequency is changed because the omega 2 that we track it's depend on the coupling, which related to the coil position. And this is the result during the battery charging conditions. The nominal voltage of the battery is 55 volts. The power rating is 1 kilowatt. The efficiency is 89% at the constant current mode and reduced to the 77% in the constant voltage mode. Conclusion, we summarize in the contribution of this work the advantages of the bifurcation of the PP compensation in the WPT system are provided. From the mathematical analysis, the voltage and current gains are independent from the coupling and load. The secondary voltage of the PP compensation under bifurcation offers higher voltage that is compatible to supply the electronic loads on the secondary side. In this case, we use the onboard charger is as an load on the secondary side. With the coupling independent operation, the proposed method can be adopted to accommodate various coil configurations. The identification method and control of the secondary voltage under bifurcation using only the measured voltage and current on the primary side. This method is simple, low cost, and easy to implementation. In addition, the secondary voltage can be directly controlled through the primary voltage based on the primary side control. This reduces the cost, size, and complexity of the WPT system since it does not require additional sensors or communication device and controller on the secondary side. And this is the publication. Thank you.